getting started today, I'll quickly go over the leftover lecture notes, which are method we use to determine the molecular structure of polyatomic molecules. So you'll see all these methods like vibrational spectroscopy, NMR, which is nuclear magnetic resonance spectroscopy, and mass spectrometry again in organic chemistry if you stay long enough. But today I just want to give you a quick overview on how these methods are used and what kind of information they provide you. So we're not going to go into great detail about the spectroscopy or spectrometry method. The take-home message of this lecture is trying to understand what kind of measurement we're taking and what type of information we're getting by doing those measurements. So nothing too quantitative for all these three topics here. All right, so we finished talking about the traditional optical absorption spectroscopy, so I'm just gonna jump forward. First topic here, vibrational spectroscopy. So like we said in our last lecture when we talked about vibrational spectroscopy, what it tells us are information including like bond force constant or how stiff that bond is, and then together, what we're getting are information about a specific chemical bond. So vibrational spectroscopy, like what we said, uses like near infrared region, or in organic chemistry, we normally just call it IR spectroscopy. So that's a quick review of what we talk about in vibrational spectroscopy. And IR spectroscopy tells us lots of information about what are the functional groups in an organic molecule or in a complex molecule in general. So what are functional groups? Typically, when we talk about functional group, they are just part of a very complex molecule that has very distinctive chemical properties. So we'll use acetone as an example. So as we see here, acetone has two different types of functional group. The yellow part here is called methyl functional group. The green part here is called carbonyl functional group. I don't expect you to know it. I'm just saying functional group is, say, these carbonyl, the CO double bond in a complex molecule. We call it a carbonyl functional group. And infrared spectroscopy is very good in identifying these special functional groups. When I say I don't expect you to know it, I don't expect you to assign names to different functional groups. You'll learn that in organic chemistry. But I do want you to know what is a functional group when we talk about it. And using the infrared spectroscopy, the vibrational spectroscopy, we can identify the existence of these functional group in a complex organic molecule. We'll see an example very soon. So that's the first piece of information, functional group. And just as a quick extra item, so this one is not on your final, so you can take a break if you like. But in polyatomic molecules, vibrational motions in general are actually superposition of different normal modes. So when we say normal modes, what we have are, depending on the symmetry of your molecule, you can have different single type of vibrational modes. And what we observe on the IR spectroscopy, on the overall spectroscopy, is actually an overlay of all these normal modes adding up together. So that's why spectroscopy is more complicated than they appear to be. So if we use water as an example, it looks very simple. We only have 3 atoms. We have 3 different types of normal mode that can actually overlay together. So for example, I'm showing here, that's a symmetric stretch, means your hydrogen is like symmetrically stretching at the same time. So these animations are actually calculated using quantum mechanical methods. So that's a symmetrical stretch. You can have also anti-symmetric stretch. So it's still a stretching, means when we see stretching, we're talking about the oxygen and hydrogen bond that's getting longer and shorter. But in this case, in the anti-symmetric stretching, it's moving in different directions. So that's why it's called anti-symmetric. On top of the 2 stretching normal mode, we also have a bending normal mode, where in this case, the hydrogen atom is like going up and down. So depending on what kind of force you have in your molecule, the reality is even if we draw everything on paper, we did that a lot when we draw water, when we draw Lewis-Dot diagram, or we use valence bond theory to depict the chemical bond. The reality is that your molecule is always stretching or bending. There's always lots of molecular motion that's going on. So whenever we draw it on the paper, what we're drawing is like a likewise or an average structure of that molecule. So in reality, your molecule is always like vibrating or stretching, as long as we have some temperature available. So that part's just an extra, just to show you some nice pictures in what we're actually measuring when we're taking a IR spectroscopy. So what I expect you to know is we know that using IR spectroscopy, you can identify different functional groups in a complex molecule. So if I give you a table like this, what it contains is on the left-hand side, we have different type of chemical bonds. You can have a CO double bond, a CO single bond, a OH bond, or just a CH sigma bond. All these chemical bonds, they would have different range of frequency, and they are expected to have different absorption intensity. So by reading the table, we will be able to derive some information about an organic molecule. So I'm just going to leave this table here for your reference. So these will be provided information, and we'll do an example together and see how are we using the table to identify these functional groups in a specific molecule, or to assign peaks to that specific molecule. Let me just remove all my notes because it's a little bit cheating. So in this molecule, let's see what we have here. On the top is the molecular structure. This is already identified. This is a little bit like cheating, but what I want you to do is make a connection between this molecular structure and the actual IR spectrum, so that in the future, without knowing that molecular structure, you can just read the IR spectrum and get some information about that organic molecule. So a few things we want to look at is, first of all, on the x-axis, that's the intensity. So the information is here. The higher the peak it is, the larger the absorption intensity we expect it to be. And then on the x-axis, that's the frequency range. So note that frequency range is in wave number, and here in the table it's also given in wave number. And you can read the frequency range and find out what kind of functional group it is. So a few things, let's just do some quick example here. We'll just do two, and then you can work on it yourself. Let's use this carbonyl group here, or the CO double bond. So if we read the table, we expect the CO double bond to locate in the frequency range of 1820 to 1630. So 1820 to 1630, that's about that area. So what we have is this large peak here with very high absorption intensity. We expect that to be our CO stretching. The CO double bond stretching. And then in our molecule, we also have the CO single bond, which is this chemical bond here. And that's in region of 1000 to 1250. And it has relatively strong absorption intensity, so that's here. So you can work on it yourself. And I just want to quickly show you what the stretching actually looks like. So here are some of the figures again. On the left-hand side, we have the CO stretching. As we said before, you can see the primary vibrational mode is the stretching of that carbon and the single singly bound oxygen, right? So the primary mode is the CO stretching, but you also have other groups that's also vibrating and wriggling around. So the reality is complicated, but we try to simplify it. Likewise, the carbonyl group or the CO double bond stretching, we see that the primary case here is the CO double bond stretching, but the other part of the molecule is also moving, that's accompanying that stretching. That also explains why on this table we have a big range for that frequency instead of just one single line. Nevertheless, so that's the IR spectroscopy. The take-home message here is in organic chemistry. We use IR spectroscopy by looking at the table and identify key functional group in an organic molecule. All right. So that's our first tour to have. Second tour is called nuclear magnetic resonance spectroscopy. So again, this one, my expectation to you is very qualitative, understanding the general theoretical background of NMR spectroscopy, and very quickly know how to read super simple NMR spectrum. You'll learn that in organic chemistry. You'll spend like 3 to 4 lectures on that if you're taking 14 series. So, NMR spectroscopy. What are the theoretical backgrounds of the NMR spectroscopy? Like what we said in electrons, we were talking about there exists a fourth quantum number, which is spin. So like electrons, some of the atomic nuclei also have spin. So what does spin mean? So here I added another figure illustration on what spin actually means. So these spin are little magnetic dipole, if you like. So without an external magnetic field, your spin or your little magnet is oriented in a random fashion. But with an external magnetic field that's pointing to a certain direction, atoms or nuclei or electrons with different spin will react differently when there exists an external magnetic field. So depending on how your nuclei or how your electron react to that external magnetic field, we can distribute them into 2 different types of particle, one spin up, one spin down. All right, so that's a quick review. We spent some time talking about electron spin before. Now the new concept here is that like electrons, nuclei can have spin as well. So, because your nuclei has spin, apparently we can use that characteristic to identify different types of nuclei, or to at least get some information about the position of those nuclei. So a quick experimental setup, I'm not gonna test you on that, but what we have is we have a sample, and then we have a huge magnet that's surrounding it. And then for nuclear magnetic resonance, we only need radio wave to do the measurement, but we're using very strong magnetic field. So what happened is we have that strong, uneven magnetic field acting on the sample, and then nuclei with different spin will react differently to that external magnetic field, leading to the NMR spectroscopy. I know it doesn't make any sense, so let's just put it on a quick picture here for your reference. So what it makes is before we have the magnetic field. Remember, your nuclei with different spin are randomly organized. So they all have the same energy level called E0. So that's the chaotic mixture without any external magnetic field. Your nuclei with different spin are mixed up with each other. And then when we apply that external magnetic field, depending on if your nuclei spin is aligned with that external magnetic field or against that external magnetic field, now we have a split between these two particles. All right, so depending on how your magnetic field, whether it's aligned with your nuclear spin or works against the nuclear spin, you can have two different, you can have that splitting in the energy levels. So with me so far? So this goes back to this original picture. So that is our E0. That means without magnetic field, they're all mixed together. And then with the magnetic field, if we have spin up, so it's working with the magnetic field, we expect that to have a relatively lower energy. And if your nuclear spin is working against that external magnetic field, we expect it to have the high energy. And what we'll measure in the NMR spectroscopy is the delta E, or the energy difference between the spin up and the spin down nuclei. Right? So coming back to the energy diagram, what we're measuring here is the delta E between these two energy states. And here, that h mu, where mu is our frequency, where in this case we're using radio wave, so the mu is relatively small, times Planck constant, well, h mu gives you energy. And here are some of the parameters we have for our NMR spectroscopy setup. Or in more general, you can imagine this Gn and mu n term to be constant, you don't need to know. And then B naught gives you the magnitude of the magnetic field that's applied in your NMR study. All right, so that's what we're measuring. But how does this information tell us about the position of the nuclei or the relative geometry of your molecule? So that comes to the second property of these nuclear spin. So when we measure the nuclear spin, these are spins that are highly sensitive to the chemical environment of the nuclei. So when we talk about nuclei with spin equals to 1/2, means you have like spin up and spin down. Remember, our electrons also have spin of 1/2. So the consequence there is that if you have electrons that's surrounding or neighboring to your nuclei, these neighboring electrons can create what we call a local effective field and shield the nuclei from the magnetic field. So in chemistry, we use chemical shift to describe a NMR nuclei in a specific structural environment. So the way to calculate chemical shift is, in general, chemical shift is a relative value. When we talk about chemical shift, what we're talking about is how much a sample or how much a target nuclei is shielded. Is it less shielded or more shielded comparing to a reference compound? So in here, that's the chemical shift. Bs, that's the magnetic field strength of the sample, minus Br, that's the magnetic field strength of the reference. And remember, these B are the magnitude of the magnetic field. We can get those information by reading the spectroscopy, because delta E equals h mu equals to constant times B. We know the frequency we're using, and we have all the constant, we can solve for the magnetic field strength. So that's the more quantitative picture of the NMR spectroscopy. And then we'll look at a very quick example in how organic chemists use the NMR spectroscopy to determine the structure of a molecule. So when we have the proton NMR, when we say proton NMR, we're just measuring that. We're trying to find information about that proton. We're using the proton NMR of chloroform, or CHCl3, and comparing that with TMS. So by just looking at these two molecules, it is quite straightforward that in chloroform, on the left-hand side, we have less number of neighboring nuclei to shield that hydrogen of interest. And on the right-hand side, in comparison, in my TMS, we have more neighboring nuclei to shield the hydrogens. Or on the actual NMR spectroscopy, what we have is a figure like this. So the TMS is our reference. We'll manually set the peak for TMS to be 0. It is more shielded, and we call that more upfield. So the smaller your ppm is, the more upfield it is. And then on the left-hand side, we have larger ppm, means that hydrogen is less shielded. It's more of a downfield position. I'm never going to ask you to solve the spectrum. I only asked you to know the very fundamental of NMR, what we are measuring. We're measuring the nuclei spin. And how we're measuring it is we apply the magnetic field onto these nuclei, and the nuclei react differently. And that energy splitting is what we're measuring. And with that energy splitting, we are getting information about that local magnetic field strength. And by working out that local magnetic field strength and comparing it with a reference point, we can get information about the molecular geometry of a specific atom. You'll work on that a lot in organic chemistry, but in this point, I want to introduce you the theoretical background of NMR. Yes?
When you said the electron spin can affect the spin of the nucleus, did you mean the electrons of neighboring atoms? Or?
Yeah, the electrons of the neighboring atoms. I know it is weird, but it is electrons of the neighboring atoms that's affecting the spin. I mean, the downfield versus upfield. All right. The last topic I want to talk about is mass spectrometry. So mass spectrometry, it's not spectroscopy because we're not using light anymore. What we're doing in mass spectrometry is we're trying to start with a molecule, and then you use high energy electron beams to knock that molecule into different iron parts. So we're forcing that molecule to break into smaller pieces, if you may. And then after that molecule breaks into smaller pieces of different ions, it will pass through this bented curve or tube, if you may. And in this bented tube, we have a magnet set up in position. So depending on the molecular weight of your fragment ions, they will bend differently and reach your detector at a different speed. At the end, what we're getting on the detector are information about the molecular mass of different fragment ions. So if it is a very complicated molecule, you can imagine it breaks down into a lot of smaller pieces you can solve for. It's like playing a puzzle. How do you put those puzzles back to a molecule? For this class, I'll just use the diatomic molecule as an example. So in these measurements, what we're focusing on is how do you read the mass spectrometry, and to get information about isotopes of these atoms. So, for example, if we're talking about oxygen, or O2 here, when it passes through that mass spectrometer, what we're getting are two different peaks. It's oxygen, we only have two possibilities. The first one is the O2+, so that's called the molecular ion. it gives you information about the molecular weight of the oxygen molecule. And then here at 16, what we have is just a single oxygen atomic ion, and that gives you information about the atomic mass of oxygen. So since oxygen doesn't have much stable isotopes, we only see one peak on the spectrum here. But with isotopes, for example, if we're looking at chlorine-2, reading the mass spectrum can be more complicated. So we know that chlorine has two different isotopes. You can have either chlorine-35 or chlorine-37. So isotopes are something we discussed in our first day of lecture, so if you don't remember it, I recommend it go back and review it a little bit. And then because chlorine have two different stable isotopes, what we observe on this mass spectrum are actually 5 different peaks. And what these 5 different peaks are, you can read it by looking at the mass of these peaks. So apparently you can have chlorine-35 with 35, so that's molecular weight of 70. Molecular weight of 72, you have 35, 37. And 74, you have 37, 37. And likewise, on the left-hand side, you have 2 different peaks for the atomic chlorine, can be 35 or 37. So the take-home message of this last part of our entire quarter is a quick overview on some of the spectroscopy or spectrometer technique you can use to determine the molecular structure of a relatively speaking complicated molecule. So IR spectroscopy gives you information about functional group or tell you what, for example, do you have a carbon-oxygen double bond in that molecule. NMR is more trivial, it's delicate, it tells you information about the environment surrounding your atom of interest. And mass spectrometry, on the other hand, gives you information about, hey, now we have a molecule and we're breaking it into parts. It gives you information about the mass of your molecule and also its possible fragmented parts. All right, so that concludes everything of this quarter that might be on the final. Before we conclude, we still have about 20 minutes. I want to introduce you to our review. But before that, I want to introduce Dr. Barr, who will be your instructor for 20B if you are taking 20B.
Howdy, everyone. My name's Chris, and I've been teaching 20B for the past few years. And first of all, I want to give her a round of applause. She's doing fantastic. But I just want to give you a little intro to get you prepared for those of you who want to, or who will be taking 20B next quarter. Just out of curiosity, how many of you are engineers? How many of you plan to get a job directly out of UCLA? How many of you want to work, or planning to go into a workplace where you'll have other people that you'll be collaborating with? Okay, so we can see the importance of working with others and having those workplace dynamics. And so as an important feature of my class, we do incorporate that. So I just want to let you know that discussion section is required because that's where the real learning happens in my class. That's where you're going to be supported by an amazing team of learning assistants. You'll be going through problems and you'll be collaborating. As much as I would love to say my lectures teach the content, at the end of the day, actually going through and working through the content is where you learn. Having conversations, because learning is a communal process. You'll need to talk to those around you. You'll need to explain your rationale. You'll have discussions. You'll have, hopefully, positive arguments of like, wait, wouldn't you want to do this? No, I think this way makes more sense. So I want you to be aware that it is required that you show up to the discussion section that you signed up for. I also want to say that great job going over the energetics and spectroscopy because that's where we're going to start. So this is chapter 20 in your textbook. We're going to start there because we can use this as a scaffold. For example, you were seeing all these nice modes that were occurring, the vibrational modes. You had the different types of stretching frequencies. Can someone give me an energy scale around any units you like? describe roughly the energies of vibrations. It was discussed today. I saw it. Any energy scale you like. Cough, cough, wave numbers. Let me ask it a different way. What part of the electromagnetic spectrum does that energy reside? For vibrations. Infrared, that is correct. And so we know that this is the energy scale when have those vibrations occur. Why is that important? Because by understanding what that energy is, we can think about, well, if we're talking about the properties of the gas of the material, how long or what energies do we need to supply it in terms of heat or radiation in order to make those vibrations occur? So understanding these scales is really important. So we're going to start where you are ending here. And then from that, we're going to continue the conversation into energy, work, connect that into thermodynamics. We'll talk about that in terms of enthalpy, heat capacities. We'll apply that into Gibbs free energy. And from there, we can go into some more fun stuff, equilibrium, where we can talk about what is the likelihood of a reaction progressing forward by looking at the equilibrium constant, saying this reaction is favorable, this reaction is not. Are there ways that we can make a reaction go forward when normally they're not favorable? Which then we can connect it to electrochemistry, which is pretty cool in and of itself. And then at that point, we're going to do transition into rates of reactions and to describe different types of reactions that would normally occur spontaneously but are limited by something. For example, for those of you who've seen diamond rings, it is actually thermodynamically stable or thermodynamically spontaneous for diamonds to spontaneously turn into graphites. Thankfully, it doesn't happen, but it is spontaneous in terms of thermodynamics. So it's one of those processes of why doesn't it happen. We'll be able to talk about things like that. And lastly, I like to have some fun, and so this is week 10, so we're having the fun topics. So we just finished talking about nuclear chemistry, and using what you described through 20A through 20B, we go into some solid state materials. Not that we're going into a lot of depth, but we're going to be using the lens of general chemistry to look at these overarching prospects so we can show, hey, your general chemistry can be applied beyond simply, here's acid, here's base. No, we can go beyond that. And we can talk about this with using the simple language of chemistry. So I just wanted to give you some of those caveats, give you some of those explanations, and let you know that before even the class starts, we're going to have, I'll have the websites posted probably by the end of finals week. Everything will be up and available for you. There is a lecture 0, which just goes through expectations and walks you through kind of how to be successful in the class. So please watch the lecture 0. If you want to wait until after your spring break and enjoy it, that's totally cool. Just wanted to convey that it exists. Before I run away, are there any questions? All right, for those of you who are joining us, I'm super excited to have you on the team, and we're going to do a lot of great things, and enjoy the rest of your quarter.
All right, so before we end today, I'm going to give you a quick review on the entire quarter in what we covered and how are these topics connected and how to understand why we start with quantum mechanics. I got that question a lot in our week 1. I have so many students ask me, why are we learning quantum mechanics in a chemistry class? So again, here's this table. I've shown it several times. It gives you a connectivity between all the topics we talk about. So this is 20A, it's called chemical structures. So we spend a lot of time talking about the first question, what is an atom? So that part, we start from the classical theory, or we're just using the Coulomb's law, or this is the Coulomb's law, the Q1, Q2 over 4 pi epsilon naught R. I hope you're familiar with it. So we start from the very fundamental classical theory of the attractive force between the nuclei and the electron, the repulsive force between the electron and the electron, etc. And then we move on to talk about why we need quantum mechanics. And the reason we need quantum mechanics is because the classical theory simply doesn't work on the atomic scale. So from that end, we introduce 3 different fundamental experiments in quantum mechanics. We have the black body radiation and introduce the concept of energy quantization. We have the photoelectron effect and introduce the idea of wave-particle duality of light. And at the end of that part, we talk about the atomic spectroscopy and introduce the Bohr model. But we want to make it more generally applicable. As we were working on the atomic spectroscopy and Bohr model, it only works for one electron systems. And what we want it to be is a more universally applicable theory. So that's why we dig a little bit deeper than your common Gen Chem classes into quantum mechanics by introducing de Broglie wave, Heisenberg uncertainty principle, and at the end, the Schrodinger equation. So we'll see a bit more information here, but the take-home message about the Schrodinger equation is by solving the Schrodinger equation, you get a wave function. And that wave function tells you everything you want to know, but you need to ask the correct question. For example, it gives you energy if you use a Hamiltonian operator to act on it. It gives you a probability distribution function or tells you what's the probability of finding your particle somewhere in space. So that's the end of the quantum mechanics part. We also talk about the hydrogen atom. I don't know why I don't have it here, but we spend lots of time talking about hydrogen atoms, including atomic orbitals. And one important concept there is atomic orbitals, like we draw it. For example, I can draw a p atomic orbitals. It looks like a cartoon, but it is in fact a mathematical function. You can solve for it. So that's the end of the first part, basic of quantum mechanics. The question we are asking is, what is an atom? And the answer to that question is, in an atom, your electrons are not only particles, they're also waves. When we say waves, what we say is there is a probability of finding that electron somewhere. And that probability is described by the wave function we solved by solving the Schrodinger equation. The wave function is equivalent to atomic orbitals. And in this class, we're only drawing the qualitative picture of atomic orbitals. All right, so that's the first part, what is an atom? And then we move on to talk about the second topic, which is what is a chemical bond? So we started easy. We talk about periodic trend. We talk about classical bonding theory, where we're treating the atoms as pure particles. And in classical bonding theory, we talk about Lewis dot diagram, VSEPR. Those are important theories, but they're not technically speaking correct. And then we try to give a more quantum-based description on the bonding theory. You have valence bond theory, you have the LCAO-MO theory. So these theories have different fundamentals. The valence bond theory, we're taking the product of the atomic orbital, of the singly occupied atomic orbitals. You might need hybridization to get enough singly occupied atomic orbitals to use valence bond theory. But using the valence bond theory, we're getting the more localized electron density in a molecule. That's the advantages of valence bond theory. But it doesn't do as well telling you information about energies of those electrons or of those chemical bonds. Alternatively, we have the LCAO-MO. So what does it mean? Several terms here. MO, that's molecular orbital. So like atomic orbital, molecular orbital are exact solutions of the Schrodinger equation if you solve for a molecule like H2 plus with only one electron. But we can't solve that Schrodinger equation for every molecule we are working on. So LCAO is just giving you an approximated molecular orbital by taking the linear combination of atomic orbitals. All right, so that's why in the LCAO-MOs, occasionally you can have like two different p atomic orbitals, you write them together, and the linear combination of it gives you a pi bond or a pi MO. So the linear combination of atomic orbital, that's an approximation we use to create molecular orbitals. So That's the second part. We talk about three different bonding theories. You have the classical bonding theory, valence bond theory, LCAO-MO theory. They all have their advantages and disadvantages, so that is why we're analyzing the chemical bonds. Normally, we can use them all together, right? And you want to know when and where to use the correct theory. And at the end, we talk about several different additional topics. We have spectroscopy, we just finished. We have chemical reactions, stoichiometry, how to balance chemical reactions. I also have the organometallic or transition metal topics. So these are more isolated topics. So that's how our corner is connected, its chemical structures. We have 10 more minutes, so I have a very super fast walkthrough on the important topics we talk about. And what's the one sentence take-home message from each of these topics? So, again, we start from classical theory. And what we have, the classical theory failed to explain some of the experimental radiations. Experimental observations, not radiation, sorry. So the two experiments we talk about is blackbody radiation and photoelectron spectroscopy, or photoelectron effect. And that gives birth to quantum mechanics, or the two fundamental hypotheses of quantum mechanics. So in the blackbody radiation, in that entire lecture, the take-home message of the blackbody radiation is that energy levels are always quantized. So in the classical picture, when we look at the energy, you're thinking about it as a continuous relationship. It's like if I have some marker here and I drop it, the way it drops means the force or the energy associated with that process is a continuous process in classical picture. But in the quantum mechanics picture, it's a discrete process. It means when it drops, there's only like several energy levels it can take. It's not continuous. But the reason we don't see it is because these different energy gaps are really small. So in any of our macroscopic objects, we're not able to see it. So that's the first quantum hypothesis. Energy levels are always quantized. Second one, when we talk about the photoelectron effect, what we have is wave-particle duality. Again, in that experiment, what we're saying is at the surface of your photocathode, you have some kind of work function. Only if the photon energy is larger than that work function, you will observe photoelectron ejection. So that E photon is h mu. So h is our Planck constant, mu is the frequency of the light. So the nature of light, for one, it is a wave. You can have wavelengths, you can have frequency of a light, of a EM radiation. At the same time, they also act as small packets of energy or photons. So what we have is each photon consists h mu of energy. So those little packets of energy gives you the particle nature of photon or of light. So that's what we call wave-particle duality. With those two fundamental hypotheses in quantum mechanics, we introduce the Bohr's law and atomic spectroscopy. Or in general, in atomic spectroscopy, what we're asking is what's going to happen when one photon of energy is being absorbed or emitted. Right? In the absorption spectroscopy, you have that energy level, you have the sample absorb one photon of energy and jump from a lower state to a higher state. In the emission spectroscopy, you start from a higher state and you emit one photon or h mu of energy to reach a lower energy final state. I think I had that wrong here. All right, so that's the atomic spectroscopy. So when solving problems of the atomic spectroscopy, I highly recommend you write out these energy diagrams just to avoid your own confusion. All right, and then we discussed the Bohr model. I didn't do it with you, but Dr. Pham did it with you in class about the derivation of the Bohr model. So we made some quantum hypothesis in the Bohr model derivation, but at the end of the day, the Bohr model is still a simplified model that only works for 1 electron atoms. And in the Bohr model, this is the most important equation you want to remember, well, or know where to find. So that describes the energy level of any 1 electron atoms. Solving the Schrodinger equation gives you the same energy level equation. So En means energy of a specific quantum number n is negative z squared. Z is the atomic number or the charge of your nuclei over n, which is your principal quantum number n. And then we move on to talk about a more generalized quantum mechanics theory. We introduced the Broglie wave. So this is an extension of the wave-particle duality of light. In the Broglie wave, what we're saying is all particles, large or small, will have wave-like property. Like a tennis ball also have wave-like property. It just the Broglie wave associated to a tennis ball is super small. And then we introduce the Heisenberg uncertainty principle, where we're saying it's the position of a wave is not well defined. So if we're looking at the spread of position and spread of the linear momentum, when they're taking the product of those two spread, you will have a value that's always larger than or equal to h over 4 pi. And at the very end of our first set of topic, we have the Schrodinger equation. Like what we said before, the Schrodinger equation is a differential equation. What is said is using this Hamiltonian operator or that differential equation on the wave function, what you're getting is the energy times your wave function. So if you're taking linear algebra in your future classes, this Hamiltonian operator is more or less a matrix, and this energy is the eigenvalue of that matrix. So you'll see that in your linear algebra classes. And then for any differential equations, boundary conditions gives physical meaning to that differential equation. So in the Schrodinger equation, when we talk about the physical meaning of the Schrodinger equation, it is by definition, the wave function is a probability wave. Or by definition, the absolute value square of the wave function gives you the probability density. And when you take the integral of that probability density through all space, it must add up to be 1. Right, so the nature of our wave function here, it is a probability wave. And the reason is by definition, because of the boundary condition, we call it a probability wave. It gives you position on the probability distribution in where we can find that particle in space. So for the wave function and the Schrodinger equation, we spend some time solving the one-dimensional particle in a box and then applying the Schrodinger equation to hydrogen atoms. And for the hydrogen atoms, we introduce the idea of the 4 quantum numbers. Right, so the first 3 gives you a quantum state or an atomic orbital or a wave function. You have quantized energy level and the principal quantum number n associated with it. You have quantized angular momentum and the angular momentum quantum number L. So here are some of the selection rules for your quantum number. For example, your quantum number L must be smaller than your quantum number n. And then for the angular momentum quantum number, you have different allowed magnetic quantum number. So for that question, for example, why do we have 3 p atomic orbitals? That's the question on midterm 1. So the reason is like buried deep within the selection rule of your quantum number. All right, and I don't think I have enough time, but I'll post this document online. So it basically gives you a quick summary on all the topics we talked about this quarter. And that's the end of today. And do remember to finish the year, the quarter end evaluation. And once you do that, go on Canvas and do that survey to get 3 extra credits. Anyway, thank you very much for this quarter, and good luck with your studying.